Okay, so yesterday we talked about work and how forces cause changes in energy. And so today we're just going to talk about that a little bit more. So when, just as a refresher, so when there's a force being applied to an object, forces accelerate objects, so they change their state of energy by accelerating them. And so forces will do work. In terms of how they're changing energy, because if they're doing work, they're changing energy. It's not changing energy, like it's not creating energy or destroying energy. It's not giving it new energy and then taking or like getting rid of it. It's all energy comes from somewhere. Okay, and that's just really short here, the law of conservation of energy. Okay, and we'll talk about this more later. But it states that energy cannot be created nor destroyed. It can only be transformed from one type into another. Okay, so if you were to lift an object off the ground, you're giving it potential energy, but that potential energy comes from you. Like you lose energy to give an object energy. Okay, so you're not creating that energy, it's coming from you, like your breakfast and all that stuff. Okay. And so like if you were to push a block along the ground and you're giving it energy, well, again, you're pushing it, so that energy you're giving it comes from you. Okay, it's being transformed from one type into another. So that's just to say that like when I'm talking about, like, keep in mind that work is EF minus EI. This is going to be like, technically, if energy cannot be created nor destroyed, then the final amount of energy in the system has to be the exact same as the initial energy in the system, because you're not creating or destroying any energy. It's just a transfer. So technically, that amount of energy is the exact same. But when I say work is a change in energy, it's a change in a specific type of energy. It's not overall energy, it's a specific type of energy. Specific type of energy. Okay, so it could be a change in EK or a change in EP, but it's not going to be both. Okay. Well, it could be both, but it's not all the energy. That's what I'm trying to say. Work energy theorem. So we have this equation where we have work equals force times distance, and this is the force that's doing the work. Well, that's just one force. Okay, if you imagine a free body diagram of something moving along the ground with an FA and an FF, and let's say V is constant, I'm just going to write A is 0, because if A is 0, V is constant. Okay, well then FA equals FF, because it's balanced. There's no net force, so that each force is balanced. And so my F net would be 0. F net equals 0. Well, that means that if I were to say, okay, work equals FA times D to find the work that the FA is doing, let's say this is 100 joules. Okay. Well, the work that friction is doing is going to be negative 100 joules. Okay, it's taking all the energy away. And that's because the delta EK in this case is going to be 0. Okay, because if the A is 0, the V is not changing. And if the V doesn't change, EK being 1/2 mv squared, if the V doesn't change, then the delta EK is 0. Okay, and so you can kind of connect the two where your individual forces are doing work. But if you were to actually expand this and say the net work being done would equal the F net times D, this would be 0 equals 0 times D. Okay, because the net force is 0, and therefore the net work is 0, because the overall change in energy on the object is 0. Okay, the overall change in energy is 0. And that leads us to this work energy theorem. It's sometimes called the kinetic energy work principle or something like that. It's the net work done on an object will directly lead to a delta EK. Try that again. Okay, so if there is no acceleration and v is constant, then net work will be 0. Okay, because whatever positive work you're doing, positive work, is going to be lost to negative work. Okay, and these aren't vectors, they're scalars, but it's an input of energy and then an output of energy. Okay, it's you're giving something 100 joules and then friction's taking 100 joules away. Any questions about any of this? I guess we should do examples first. Okay, so let's do some examples. First one's really easy. Karen is 62 kilograms and can run at 6.4 meters per second. How much energy does Karen have when running at the speed? So how much energy? Well, it's not asking what type of energy, but we should realize that, okay, we have mass, we have velocity, that's EK. So EK equals 1/2 mv squared. And then we're just going to plug that in. 1/2 times 62 times 6.4 squared. Times 62 times 6.4 squared. And that is, well, let's just call it 1,300 joules. Okay, that one's easy. Number 2, and stop me if you have questions. Kimmy is 43 kilograms and climbs a flight of stairs 14 meters to the next floor in 3.2 seconds. How much energy does Kimmy have when she climbs the stairs? This one's a little bit more tricky, but not really. So again, it's asking how much energy, and so we need to figure out what types of energy are at play here. Now, she is moving, okay? She's climbing the flight of stairs 14 meters, but it doesn't say anything about changes in velocity. Okay, if her initial velocity is whatever number and their final velocity is the exact same number, then there is no delta EK. Okay, and so the only thing that's changing is her height. Okay, she ends 14 meters to the next floor, and so what happens is she has a change in EP. Okay, her EP initial, she's on the ground level, so it's 0, and then her EP final is whatever her MGH is on the second floor. Okay, so in terms of this one, instead of doing, well, I guess it doesn't really matter. It's just asking how much energy does she have, so we don't have to do the work. So all we have to do is plug this in. So 43 times 9.8 times 14. 43 times 9.8 times 14, which is 5,900 joules. Okay, so that's how much energy she has on the next floor. And in terms of potential energy, it does not matter how the object gets higher. Okay, it can be upstairs, it can be up a ramp, it can be straight up, okay, it can be whatever, it doesn't matter. The only thing that matters is comparing the initial to the final. Okay, initial, final, initial, final. Okay, so potential energy doesn't care how it gets there. Number 3, how much energy is required to change the velocity of a 1,400 kilogram car from 14 kilometers an hour to 100 kilometers an hour? Kilometers per hour isn't going to work for us because it has to be meters per second. So as I showed you with the units up here, okay, remember that it has to be kilograms meters per second squared. So it can't be kilometers per hour. So we need to change that. Hopefully you learn this in physics 11. So 14 divided by 3.6, which is 3.89, and this is 27.8. Okay, so again, does anyone not know how to do that? Change kilometers an hour to meters per second. Okay, so this is the 3.6. Remember to divide by 3.6. Okay, so how much energy is required to change the velocity? So we have a delta EK. So we have EK final minus EK initial. Okay, that is the work required. Okay. So EK final, we're going from 14 to 100. So we're going from, we're speeding up in this case. Now, in order to speed up, there needs to be an input of energy. So my answer should be positive, okay, because energy is going into the system, into speeding up the car. Okay, if it was the other way around, saying the car is slowing down, well, then you're taking energy away from the car, which means it's going to be negative. Okay. So in this case, EKF is going to be 1/2 times M, so 1400, times VF squared, because it's final, so 27.8 squared, minus, and then again, EKI, 1/2 times 1400, I'll put brackets around this too, times 3.89 squared. Okay, now you those of you who are math inclined should be able to see this, that you can factor out the 1/2 times 1400. Okay. And so if you do that, you'll be left with 1/2 times 1400 times 27.8 squared minus 3.89 squared. Okay, so you're just factoring out those first two terms. So I'll do that part first. 27.8 squared minus 3.89 squared times 700. And the answer is 5.3 times 10 to the 5 joules. Okay, and your answer comes out as positive. Okay, and it makes sense that it comes out as positive. You like mathematically, when you set this up, it comes out as positive. But if you think about it, you need an input of energy, so it should match that. And if it was the other way around, if it was 100 to 14, well, then it would be 3.89 minus 27.8. And so that would be a smaller number. It would come out as negative. So the math should work out that your answer comes out as negative or positive if it's an input or a loss of energy. So yeah, but you also can think about it as a loss or a gain. And then the last one, how much energy is required to lift a 10 kilogram object 4 meters off the ground? There's two ways you can do this. There's the force way, and then there's the change in energy way. So I'll show you both. So if we go based off of work equals F times D, because it's asking how much energy is required, so how much work is done to lift a 10 kilogram object. If we do that, we need to look at what's at play here. So if the object is on the ground and we're lifting it upwards, the FA that you're using to lift up is opposing gravity. Okay, so you're working against gravity. Now, because you're lifting it off of the ground and it's starting at 0, V equals 0 here, and you're lifting it to a point here where V equals 0 as well, there is no delta EK. There's no change in velocity. Okay, obviously you have to accelerate it to move it upwards, but because the state of the velocity doesn't change, you can like imagine this as a net force of 0. Okay, so that means that FA equals FG. Okay, if there's no delta EK, that means there's no delta V. If there's no delta V, then A is 0. If A is 0, F net is 0. Okay, so you kind of have to play that game of like drawing conclusions based off of the different states of energy. Okay, so if that's the case, then work equals FA, which is doing the work. But because FA is equal to FG, I can just say FG times D, so mg times D. Okay, I know it's confusing, but the next way will make more sense. Okay, so if that's the case, then I can just go 10 times 9.8 times 4, which is 392 joules, I think. Yeah. Okay, so that's the way you do it with the force that's working against gravity. If we do it like this, where it's a delta E P, okay, because the object is starting on the ground and then ending 4 meters above. So initially it's on the bottom where EP initial is 0. And then the final position is where EP final is mgh. So if that's the case, delta EP, so work equals EP final minus EP initial, which we already know is 0. So work equals EP final, which is mgh. Well, if you look at the two formulas, we have mgd on one side and mgh on the other side. They're the exact same thing. Okay, so if you do it both ways, you'll still get the same thing. Now, this way is the preferred way because it'll never lie to you. This one, you might get the wrong force. You might mess up forces, net force, like the whole dynamics part with drawing free body diagrams and stuff like that. But if you look at the actual state of energy, you'll never go wrong. Okay, because that's the work being done. The whatever energy something has at the beginning compared to the end, whatever the difference is, that's your work. Okay, so you'll always get the right answer if you're looking at energy. Okay, so if you're, and I'm showing you both ways because it doesn't matter, you'll get the right answer either way. Okay, if you do it right both ways. I guess that's true for everything. If you do it right, you get the right answer. But yeah, the change in energy thing is the best way to analyze something because then it'll never lie to you. I don't know if that makes sense, but hopefully it does. Okay, any questions about that? Okay, because we're going to keep going. Actually, do I want to keep going? No, I don't want to keep going. I want you guys to actually work on some of this. So in the Files tab, let me show you where this is. Oh no, I still have a giant white screen because I was trying to, okay, give me 1 second. Okay, let's share this screen. It's gonna look really weird. Okay, so if you go to, I don't even have my Teams. I don't even know how to get to it. There we go. If you go to the Files tab, come on. This is frustrating. Okay, Files. Class materials, energy momentum. There is a worksheet package right here. So if you open that up. Okay, so you can do 4.1, but like anything that has like number 5 here has an angle here, that's the next lesson. So just don't do those angled ones because I gotta go over those still. But you can do, I know it's all labeled 4.1, it's really stupid, but you can do 4.1 work, you can do 4.1 EP and EK, and then a law of conservation we'll do after. And yeah, that's it. So you can work on this worksheet for a bit, and then we'll come together again at probably 10 o'clock to go over the rest. But I want you guys to try this first to kind of deal with these questions to see what's going on first. Okay, so let's do that. Let's go back to this stupid screen. Okay, any questions before I send you off? No. Okay, so at 10 o'clock, I'm going to start this meeting up again. So I'm not going to create a new meeting. I'm just going to start this one again. And so join this at 10, and then we'll go over the next stuff. and we'll answer any questions you may have.
Okay. And can you upload video YouTube on YouTube?
Can I what? Sorry?
Could you upload video this lesson on YouTube? So I can just go back and see
Oh, yeah. Yeah.
the lesson.
Yep. Yeah, I try to upload all the videos to YouTube, but sometimes I forget. But I will on this one right when I'm done. Okay, I will see you guys at 10 then.